Friends, we are going to start with the previous GATE questions solution program for the subject power systems. So we have already discussed all the theory portions with respect to power systems, and also we have done many practice questions with respect to the subject power system. So now we are going to do all the previous GATE questions asked for the GATE examinations for the last 20-25 years from the subject called power systems. So we have divided these into various chapters of power systems. So there are about 12 to 13 chapters of power systems into which the questions are split into. So now we are going to check out the chapters of power systems, and I have split the questions into these chapters. Chapter 1 is transmission lines. Chapter 2 is voltage control. So your workbook is also arranged in this fashion. So you can directly see the questions on your workbook, and you can study the solutions with respect to each and every questions that are there in the workbooks. So chapter 3 is cables and insulators. Chapter 4 is load dispatch. So that is economic load dispatch. Chapter 5 is the fault analysis, which involving the symmetrical and unsymmetrical faults and the sequence components. And chapter 6 is power system stability with respect to steady state, transient and dynamic stability of the power system. Chapter 7 deals with the various switchgear arrangements like the relays and the circuit breakers. In chapter 8 we will deal with the various kinds of power stations. Chapter 9 we will go for load flow studies of the power system with respect to the Gauss-Seidel method, the Newton-Raphson method, and also the various other conditions like the swing equation and the equilibrium criterion. Chapter 10 we will go into HVDC transmission systems. Chapter 11 is a small chapter including the per unit systems of calculation. Chapter 12 we will study the transients of the power system with respect to the open end, the closed end, and the line terminated with an inductance or a resistance, and the line terminating with a cable, or with respect to a Y junction, a T junction. Okay, so these are the various chapters of the power systems, and I have arranged the entire power system questions into these 12 chapters. Now we are going to start with the chapter number 1. And chapter number 1, you can see it is a study of transmission lines. In the theory, we have detailed study of transmission lines with respect to the parameters of a transmission line called the resistance, inductance and the capacitance of a transmission line, and also with respect to the derivations with respect to the resistance, inductance and the capacitance of a transmission line. And we have also classified transmission lines into short line, medium line and long transmission lines, and we have did various modeling with respect to this, and we have also made ABCD parameters and everything with respect to these lines, and we had a detailed study about this chapter in the theory portion, and also we have done some practice questions based on this. So now we are going into the previous GATE questions from chapter 1, transmission lines. Now this is question number 1. Okay, so in question number 1 we are going to check the inductance of a power transmission line increases with. Okay, so the question is like inductance of a power transmission line increases with. So we know that the parameters of a transmission line are resistance, inductance and capacitance, and here the question is with respect to inductance of a power transmission line increases with. So we will have to write down the expression for inductance. So what is our inductance expression? Inductance is proportional to Ln D divided by R dash. So that means the inductance is proportional to D, and it is inversely proportional to 1 by R dash. So what is our choices? Our choices are decrease in line length. Now the inductance of a power transmission increases. There is no relationship with respect to the length of the line. So it increases in diameter of the conductor. It increases in spacing between the phase conductors. So the inductance of a power transmission line increases with this. What is the question? So increase in load current carried by the conductors. So we will have to conclude with an answer. So the inductance increases with the diameter of the conductor. It increases with respect to spacing between the phase conductors is what is the option. So our options given are inductance is directly proportional to D. What is D? D is the spacing between the conductors. And what is R? R is the radius of the conductor. And what is R dash? R dash is the geometric mean radius of the conductor. So inductance increases with the spacing between the conductors. So inductance increases due to spacing between the conductors. So we will go with the option C for question number 1. Now moving into the next question. A three-phase overhead transmission line has its conductors horizontally spaced with the spacing between adjacent conductors equal to D. So we are considering a horizontal spacing of conductors with the spacing between each conductor equal to D. If now the conductors of the line are rearranged to form an equilateral triangle of side D. So the conductors are now rearranged to form an equilateral triangle, and the equilateral triangle is having each side D. Then average capacitance and inductance will increase. Average capacitance will increase and inductance will decrease. Average capacitance will increase, and so we will have to find out the variation that can happen to the capacitance and also with respect to the inductance. So you have to see that inductance is proportional to GMD while capacitance is inversely proportional to GMD. So when they are arranged in this form, what is the GMD? It is 2 raised to 1 by 3 times D. So you will have to refer to the theory portions how to find out the value of GMD with respect to the various combinations. I have given you the GMD equations with respect to all these combinations and also with respect to transposition, unsymmetrical spacing, bundle conductors and everything. Okay. So here in this arrangement, GMD is equal to D. So what happens here? So here the GMD is equal to 2 raised to 1 by 3 times D, and here GMD is equal to D. So here GMD is higher and here GMD is lesser. Okay. So what happens here? Inductance is proportional to GMD and capacitance is inversely proportional to GMD. So when GMD increases, what happens is inductance increases but capacitance decreases. So here what happens is that inductance decreases and capacitance increases. Okay. So what is happening is what is the question. So the average capacitance increases and inductance will decrease. So this is what is our condition when this arrangement is shifted to this arrangement. So the average inductance decreases and the capacitance increases. So what happens is that capacitance increases, inductance decreases. So capacitance will increase and the inductance will decrease. Option C is the answer for question number 2. Okay. Moving into question number 3. The increase in resistance due to non-uniform distribution of current in a conductor is known as what? It is known as skin effect. So skin effect, proximity effect, Ferranti effect, all these effects are discussed in detail in the theory. So you will have to check the theory portions corresponding to this. So increase in resistance of a conductor due to non-uniform distribution of current in a conductor is known as skin effect. So what is it? The increase in resistance due to non-uniform distribution of current in a conductor is known as skin effect of the conductor. Moving into question number 4. The charging current of a 400 kV transmission line is more than that of a 220 kV line of the same length. We will have to sort it out whether it is a true statement or a false statement. So the charging current of a 400 kV transmission line is more than that of a 220 kV line. So here you can see the charging current is proportional to the phase voltage. Okay. So charging current is proportional to phase voltage. So that means when it is 400 kV, the phase voltage of 400 kV system will be more compared to the phase voltage of the 220 kV system. So the charging current of a 400 kV transmission line is more than that of a 200 kV transmission line is true, because the charging current IC is proportional to the phase voltage, because what is the complete equation for IC? IC is equal to 2 pi f V phase C phase. So IC is proportional to V phase. When the phase voltage increases, what happens is the charging current also increases. Now question number 5. The surge impedance of a 400 kilometer long overhead transmission line is 400 ohm. For a 200 kilometer length of the same line, the surge impedance will still be 400 ohm, because the surge impedance is the property of the line which is not a function of the length of the line. So what is our answer? Our answer is option C, because if the surge impedance of the overhead line is 400 ohm, then the surge impedance of any length of overhead line will be equal to 400 ohm. And you have to also remember that the surge impedance of the cable is about 50 ohm. So that is about question number 5. Now moving into question number 6. For a 500 Hz frequency excitation, a 50 kilometer short power line will be modeled as. So 500 Hz is the frequency. And what is the length? The length is equal to 50 kilometer. So our 500 kilometer length, and so what is the length? The length is equal to 50 kilometers. It is equal to 50 kilometers, isn't it? And then what is frequency? Frequency is equal to 500 Hertz. Frequency is equal to 500 Hertz. So V is equal to F lambda. V is equal to F lambda. What is V? V is the velocity of propagation of the light. So it is equal to 3 into 10 raised to 8 meter per second, which is the normal frequency 50 into lambda. So lambda is equal to 6000 kilometers. The minimum 160 kilometer line is long. So that means if we are going to continue this expression into with respect to 500 Hertz of frequency, so 3 into 10 raised to 8 meter per second is equal to 500 into lambda, because this here the frequency is 500 Hertz. So it is 500 into lambda. So lambda becomes equal to 600 kilometers. So here lambda is equal to 6000 kilometers and here lambda is equal to 600 kilometers. So here if the minimum line is 160 kilometers, here it is 16 meters line is long, is the deduction that we are getting, because here lambda is equal to 6000 and here lambda is equal to 600. So that means there is a difference of 10 with respect to 6000 and 600. So what is our conclusion then? If this is the condition, then we will have to conclude the line as a long line, because when you are, what is our long line condition? Our long line is a line which is above 240 kilometers. Okay, so 240 kilometers into 50. Okay, and here it is 50 kilometers given, so it is 50 into 500, isn't it? So 50 into 500 is the length frequency of the line. So when you are going to cancel this, this will become equal to 10. Okay, so the numerator will still be 240. Okay, and then the denominator becomes equal to 500. Okay, so the length of the line is very, very higher when compared to that of the 240. So that means we will have to consider that this power line, even if it is only having a length of 50 kilometers, since it is operating at a 500 Hertz frequency, it should be considered as a long line. So that is answer for question number 6. Moving into question number 7. For equilateral spacing of conductors of an untransposed three-phase line. So we are having equilateral spacing of the conductors and the line is an untransposed three-phase line. Then we will have a balanced receiving end voltages and no communication interference. Unbalanced receiving end voltages and no communication interference. So since the line is an untransposed line, definitely there will be unbalanced receiving end voltages. Okay, so unbalanced receiving end voltages contributes to option B and option D, and this is an equilateral spacing of conductors of a three-phase untransposed line. Since the line is an untransposed line, it will definitely cause unbalanced receiving end voltages and communication interference. So we will go with the option D for question number 7. Moving into question number 8. Corona losses are minimized when? So you already know the equation for corona loss. Conductor size is reduced, smoothness of the conductor is reduced, sharp points are provided in the line hardware, current density in conductors is reduced, is what is the question. Smoothness of the conductor is reduced, sharp points are reduced, current density is reduced. So we will just check this with respect to the equation. So what is corona loss? Corona loss is proportional to V minus Vc the whole square. Also Vc is proportional to R ln d by R. So Vc is proportional to R, Vc is proportional to minus ln R. So here we can see R is the radius of the conductor. Okay. So Vc is proportional to R. So corona loss is inversely proportional to Vc or it is inversely proportional to R. So conductor size is reduced. So when conductor size reduces, corona loss increases. So this is what is our conclusion. So you can see corona loss is inversely proportional to the radius. So the radius decreases, corona loss increases. So our option, first option will not be correct. When smoothness of the conductor is reduced, so when the smoothness is reduced, also corona loss increases. Sharp points are provided in the line hardware, then also corona loss will increase. And the current density of the conductor is reduced. So we will have to check for the current density. Current density is inversely proportional to R. Okay. So when current density decreases, corona loss also decreases because corona loss is proportional to current density. Okay. So when current density is reduced, corona losses are minimized. So we will go with the option D for question number 8. Now moving into question number 9. A 220 kV 200 km long 3-phase transmission line has ABCD constants. A is equal to D is equal to 0.96 angle 3 degree, B is equal to 55 angle 65 degree, C is equal to 0.5 into 10 raised to minus 4 angle 90 degree per phase. Now its charging current per phase is to be found out. So we will have to find out the charging current per phase of the system. So what is charging current per phase? It is equal to V phase divided by XC. XC is equal to 1 divided by Y. Okay. So what is V phase given? It is 220 kV. So it is 220 into 10 raised to 3 divided by root 3 into XC. What is XC? XC is given as 0.5 into 10 raised to minus 4 angle 90 degree. So it is 0.5 into 10 raised to minus 4 angle 90 degree because XC is equal to C. So this is the C value that is given 0.5 into 10 raised to minus 4 angle 90 degree. So substituting that value into the equation, you will get the charging current as 11 divided by root 3 angle 90 degree. So 11 divided by root 3 will be the answer, which is option A for question number 9. Moving into question number 10. For a single phase overhead line having solid copper conductors of diameter 1 cm spaced 60 cm between centers, the inductance in millihenry per kilometer is what is the question. So it is a single phase overhead line of solid copper conductors of diameter 1 cm, D is equal to 1 cm, spaced 60 cm. So capital D is equal to 60 cm. So this is a direct equation. Values are given. So we know direct equation of inductance is equal to 0.2 ln D by R dash. So D is given, R dash is given because R dash is equal to e raised to 1 by 4 R. R is given because R is the radius of the conductor, diameter is given as 1 cm, so radius is equal to 0.5 centimeters, and the distance center to center distance between conductors is given as 60. So you can substitute the values into this and you will obtain the answer as 0.05 plus 0.2 ln D by R millihenry per kilometer. And when you are putting these values into this, you can see your answer will be C, which is equal to, because it is directly put, these values are directly put, there is no solution that is obtained. Here only you have to put the value of D and R. What is D? D is equal to 60 and R is equal to 0.5. Here D is equal to 60 and R is equal to 0.5. So when you are substituting D is equal to 60 and R is equal to 0.5, you will be obtaining option C. So it is 0.05 plus 0.2 ln 60 divided by 0.5. So option C is the answer for question number 10. Moving into question number 11. The corona loss on a particular system at 50 Hz is 1 kilowatt per kilometer per phase. The corona loss at 60 Hz. So you can see the corona loss is proportional to frequency. It is not directly proportional to frequency, but it is proportional to f plus 25. So what is the loss P2 by P1? It is equal to F2 plus 25 divided by F1 plus 25. So this question we have done directly while we were doing the practice questions with respect to the chapter of transmission lines. So P2 divided by P1 is equal to F2 plus 25 divided by F1 plus 25. What is F1? F1 is equal to 50 and F2 is equal to 60. So the ratio will be 1.13 kW per kilometer per phase. So what is answer? Answer is option D, which is 1.13 kW per kilometer per phase. So that is answer for question number 11. Moving into the next question, question number 12. A conductor which is 10 km long single phase conductor with a two-wire line are separated by a distance. So capital D is equal to 1.5 meters. The diameter of each conductor, small d, is equal to 1 centimeters. If the conductors are of copper, then the inductance of the circuit is. So this is also a direct question. We can directly take the equation LAB is equal to 0.4 because it is 2 times. It is 2 times 0.4 ln d by r dash millihenry per kilometer. So you have to substitute the value of d and r dash. You will be getting LAB as 2.3815 millihenry per kilometer. So how much kilometers is the line long? The line is 10 kilometers long. So multiplying it with respect to 10, our answer is 23.815 millihenry per kilometer, which is equal to option C, 23.8 millihenry per kilometer. So this is the direct equation. Okay. So it is a direct equation of a two-phase wire line. So the conductors are of copper, then the inductance of the circuit is asked. So that means we will have to find the total inductance of the two-wire line. So it is if it is a one wire, then you will go with the 0.2 ln d by r dash. Okay. So since it is two-wire condition of the total circuit, so there is conductor A and the return conductor B. So the total circuit is 2 times. So that means you will have to multiply this expression with the 2, then it becomes 0.4 ln d by r dash. So this is 0.4 ln d by r dash, substituting d and r dash and multiplying it with respect to the length of the total line, you will be getting the answer as 23.815, which is option C for question number 12. Moving into question number 13. Consider a long two-wire line composed of solid round conductors. Radius of the both conductors are 0.25 centimeters and distance between their centers is L meters. If this distance is doubled, then the inductance per unit length is what is the question. So that means the first case is L and the second case will be 2L. So that is what is the case. So Ln is proportional to, inductance is proportional to Ln d divided by r dash. Okay. So Ln, because we are going to double the center to center distance. If we are taking the center to center distance as d, then it is d and then it is doubled and then it becomes 2d. So what happens is that inductance is proportional to ln d. So ln 2d will be obviously greater than ln d. So what will be our answer? It will increase but will not be exactly double because it is a factor of ln. So it will not be exactly double, but it will increase because ln 2d is greater than ln d. So that is answer for that question. Moving into question number 14. A long wire composed of a smooth round conductor runs above parallel to the ground, assumed to be a large conductive plane. A high voltage exists between the conductor and the ground, and then the maximum electrical stress occurs at. So this is the direct question. In the theory, I have already explained to you this phenomenon of effect on the overhead conductors with respect to the earth. So this is the earth reflection case. Okay. So we have considered the effect of earth while we were discussing the overhead transmission line conditions. So when you are in the theory portion, I have already told you that if that kind of a condition is there with respect to the earth image, then the maximum electric stress will occur at the lower surface of the conductor. Okay. So this is a direct theory question that is already discussed in the theory portion. So that means the lower surface of the conductor will be at maximum electric stress. Okay. and the lower end of the conductor that will be facing the earth will be at maximum electric stress, because earth is at zero potential. So the maximum electric potential stress will occur on the lower portion of the conductor facing the earth side. So the maximum electric stress occurs at the lower surface of the conductor. So that is answer with respect to question number 14. Moving into question number 15. Bundle conductors are mainly used in high voltage transmission lines to reduce what? It is to reduce corona. It is to reduce corona. So for 15, we will go with option C, because you can see when you are using bundle conductors, the self GMD of the conductor is increased. Okay. So corona loss is proportional to V minus V0 the whole square. V0 approximately directly proportional to the size of the conductor, and hence larger the size of the conductor, larger will be the critical disruptive voltage, and smaller will be the factor of V minus V0 the whole square, and hence the conductor becomes smaller, and hence smaller will be the corona loss. So we will have to go for the larger net size of the conductor. So larger net size of the conductor can be realized by using bundle conductors. Okay. So bundle conductors are directly discussed in the theory as a factor to reduce corona. So you must go back to the theory and study the theory portions, the advantages and disadvantages of corona, and the factors affecting corona, and the methods to reduce the effects of corona. So bundle conductors are one of the biggest methods to reduce the effect of corona. So when you are using bundle conductors, the effective radius of the system increases, conductors increases, and when the net radius of the conductor increases, your critical disruptive voltage increases, and thereby the chance of happening of corona or occurrence of corona reduces. Now we are moving into the next question, which is question number 16.